Okay, let's talk about exponential growth and decay, part 2 here. I told you in the previous video, I would take a more continuous compounding approach to our problems, and that's what I'm going to do. Okay, do you remember our formula for continuous compounding? Okay, this is back dealing with money here, our financial models. We said future value was the principal times e to the rt. We always had what? R being greater than 0. This was what? This was the compounding rate, right? Remember R, we usually express that as a percentage. But remember this form? A equals PERT, P times e to the RT. Now, I claim that any exponential growth, or decay for that matter, can be written this way. Only in the case of decay here, you're actually going to have a negative value for your R here. Okay, when we were talking about money, R was always positive here, wasn't it? We weren't losing money, at least except to inflation. No, I was just teasing. Okay, the general form of exponential growth and decay is going to be like this. Okay, it's going to be, now I just called the general variable A. It doesn't mean future value. It can be amount of something. Sometimes this will be a P, whatever. Okay, A equals the initial amount times e to the kt, okay? A equals a sub 0, the initial amount, or a naught, e to the minus kt. This is for decay here. The difference between the two of these here, this looks very much like what? Where here, p has been replaced by a naught, and instead of r we have k, or in this case, negative k. When people use this situation here, they will often do this. K is always assumed positive. Okay, so since K is always assumed positive, as soon as you look at a formula like this, you can tell whether it's going to be growth or decay just by looking at the formula. Okay, that's assuming that K is positive. Okay, in the case that K is positive here, we sometimes call the little k the growth constant. And when you're dealing with a negative k here, that same k, or that k, is called the decay constant. In any case, it's always assumed to be what, greater than 0. I would point out here, just as an aside here, just to prove this. Now, if k is greater than 0 here, then e to the kt is e to the k raised to the t power. Okay. Now, if k is positive, e to the k is going to be, that's going to be greater than 1, so that you end up with growth. Remember that? Where the base is greater than 1, you get growth. Okay? However, if k is still greater than 0 and I'm doing e to the minus kt, okay, then I'm really looking at 1 over e to the k raised to the t power, because the negative exponent makes it what? Reciprocal here. Since this would be greater than 1 when k is greater than 0, and I'm dividing it into 1, I would actually get a positive number here, of course. I better have a positive value for a base, right? But that value would actually be between 0 and 1. If I've got 1 and I'm dividing it by a number which is greater than 1, I get a value which is less than 1, right? Okay, still positive, though, for the bases themselves. Okay, exponential growth, exponential decay. Okay, let's go ahead and revisit a problem we did previously in the previous video. Okay, and I'll do it this way, using the continuous compounding approach. Okay, the population of a city is expected to triple every 20 years. The city currently has 10,000 residents. How long until the population reaches 50,000? T we said is time in years. P of t is the population in t years. P naught is 10,000. That's p at time 0. We can come up with this formula then. P of t is 10,000 times e to the kt. Okay, so I'm using this approach this time. What we need to do is what? We need to find what k is. Now, k is going to be a positive number because we know it's what? The population is growing. Now, how do we actually find what k is? Okay, this is essentially what we need to do here. Once we know what k is, we've got a formula for p for, in theory, for all time here. Okay, p at 20 should be what? 3 times what the 10,000. It should be 30,000, right? So we've got a point here on our graph where we've got p of evaluated at 20 years should be 30,000. I hope that makes sense, right? Population triples in 20 years, and initially we had 10,000. So this should hold, okay? So that means this, with substituting p equals 20 in this formula, I would get p of 20, which is the 30,000, is 10,000 times e to the 20k, k times 20, which I wrote as 20k, okay? Now I'm going to divide by 10,000 on each side. I would get 3 here. There's our tripling, right, in 20 years. Okay? Do you see the idea of tripling every 20 years here? We got to find what k is. Okay? Can you see what k would be? Okay? This would be 20k is the natural logarithm of 3, and then k would be the natural logarithm of 3 divided by 20. Now, for a constant like k here, you want to take that to several decimal places, okay, because your function is sensitive to changes in the exponent here. So I'm going to go natural logarithm of 3 divided by 20, and I'm actually going to go to 4 decimal places here. I get 0.0549, okay? So here is our growth model. 10,000 times e to the 0.0549 t, okay? So now we know we've got an equation for the population as a function of time, and let's go ahead and use this to answer our questions here. When is it going to be 50,000? Oh, I might throw this in here since this is acting like what? A compound interest rate, and this time is in years. This is like almost 5.5% interest compounded yearly. That leads to the tripling every 20 years. Okay, now here's what we want to do. We wanted to find t when the population was 50,000. So we're going to go like this. 50,000 is equal to 10,000 e to the 0.0549 t, like that. Makes sense? Okay, divide on each side by the 10,000. You see we've got 5 on this side, is e to the 0.0549 t. Okay, rewrite that as a logarithmic equation. Okay, the 0.0549 t is the exponent. The base is e, as you can see, so we're looking at natural logarithm of 5. Remember how we don't usually write logarithm base e instead. How do you get t? And you're going to divide that by 0.0549. Okay. Okay, so let's do that on our calculators here. I'm going to use my rounded value rather than, I do have the exact value written above here. 29.3. Okay, 29.3, and that was in years, so you want to include the units there. I'm rounding time to the nearest tenth, though I probably should have mentioned that. Okay, this is the exact same answer we had in the previous problem, where instead we were using a slightly different approach. There, if you remember, we were going 10,000 triples every 20 years. I personally like this approach better. I can look at the parameters of the problem immediately and just go boom. Right. All right, but we want to see it multiple ways here. Alrighty? Alrighty, let's look at another problem here. This is how it looks fun. The rodent population in a city rose from 20,000 to 30,000 in 1 year. Now we're going to assume exponential growth. How long until the population reaches 100,000? Okay, Joy. T is time in years. P is the population of the rats here in T years. Okay, I'm using an initial population, so I'm measuring my time from the time when it was 20,000. The population was 20,000. So P naught is P of 0 is 20,000. P at 1 is actually 30,000. We have that bit of information here. Okay, so we're going to use this model. P of T is 20,000 times e to the kt, right? We know k is going to be greater than 0 here. Okay, it always is in these problems that we're going to be looking at. Okay, really good. Okay, now we said 30,000 is P at 1, but if I let T equal 1, I should say, I get 20,000 times e to the k times 1, which is really k. That's okay. So let's go ahead and divide by 20,000 on each side. 20,000 goes into 30,000 1.5 times. So the point is it grew by a factor of 1.5 in 1 year. So we've got 1.5 is e to the k. That implies that k is the natural logarithm of 1.5. And what should that be approximately? Okay, let's use our calcs. Okay, better be a positive number. Okay, quite a bit. Okay, this is about 0.4055. Again, I'm going to round to 4 decimal places. Okay, that's what I get on mine. Alrighty. So what is the law of growth for the rat population? P of t is 20,000 times e to the 0.4 t. Okay, so I just took that k and stuck it in the formula there. I'll box that in as a major result here. Okay, 40% growth in 1 year, essentially compounded. Okay, how long until it reaches 100,000? Okay, well, what are we going to do there? We're going to go like this. We'll say the population is 100,000. Okay, and we're looking for a t. Okay, this is what our original was 20,000. And e to the 0.40. What was it? 55? Yeah, double check, make sure. T. Okay, that's what we're looking at. Okay, let's isolate the pure exponent part. Let's divide on both sides by 20,000. How many times does 20,000 go into 100? Okay, so we're wondering how long it takes to grow by a factor of 5. Okay, alrighty, so this is what we're looking at. You can see that this reduces to this equation, right? Okay, and that t is therefore the natural logarithm of phi divided by 0.4055. Let's crunch that out here. We've got natural logarithm of 5 divided by 0.4055, and I've got 3.96. Okay, if I was to round to the nearest tenth of year here, right, I would add 1 to this and I would go 4.0 years. Since I'm rounding to the 10th, I still write the 10th, indicating to people not just the value, but also how far I rounded. Okay, we talked about that before. Okay, so it looks like about 4 years. And the rat population is going to be pretty bad. Okay? All right. Somebody called the Pied Piper here. Okay, let's do one where we've got decay here. You guys remember radioactive decay is kind of a classic example here. The half-life of a certain radioactive material is 15 days. If 10 kilograms of the material is present initially, how long until 1.2, yeah, this is 1.2, kilograms is present. Okay? All right. Now, here's what we're going to do here. I'm going to say t, what's first of all? T is time in days this time, right? Because the half-life is given in terms of days. So let's go ahead and use that time period. Okay? All right, let's see the amount present originally. A is the amount after time t. Amount after, I should probably say amount in kilograms. I guess I'll do that now. Kilograms after t days. It's not like anybody get mixed up here probably, but let's go ahead and do it. What's the initial amount? That's A at time 0 was 10 kilograms. Okay, 10 kilos. All right. All right, let's go ahead and write what's going to happen here. A, as a function of time, is going to be your initial amount, right, times e to the, is this correct, k, t? No, because we're dealing with a decay problem, and we always assume that k is going to be positive. We put the negative sign out there. This will keep k itself as a positive number. When somebody looks at that, they're going like, oh, that's a decay problem because of that, assuming k is positive, like usual. Okay, so we've got to do this. Okay, now let's go ahead and remember that the half-life is going to be 15 days. So this means, well, what's half of 10? Is 5. Okay, 5, again, this is going to be in kilograms. I'm not going to write everything. Is going to be present after 15 days, right? 5 is the amount after 15 days. So that should be, what, 10 e to the... I'm going to, instead of writing K15, I'm going to write 15K there. Usually write the number before the variable here. Okay? All right. Now, if I divide on both sides by the 10, I get 1/2. Okay? Now, this makes sense. Where'd the half come from? Well, I'm using the fact that it's a half-life, really. Okay? Okay. And then we got like that. Okay? Look good? So, the 1/2, or the 0.5, if you prefer, 0.5, is e to the minus 15k. Now, what's k going to be? K is going to be the natural logarithm of the 0.5 divided by negative 15. Okay? Now, what we're going to find is the natural logarithm of 0.5 is actually a negative number also. So when I'm dividing that by another negative number, I get a positive k. Okay? Let's do that. Let's see that. I'm actually going to put that number in there so you can see it. 0.5. Okay? See, it is a negative number, negative 0.693. Then I'm going to divide that by negative 15. Okay? And I get 0.0462 to 4 decimal places. Okay? All right? So that's our k. Now let's write the law of our growth here, or I'm sorry, decay. And what is it? A as a function of time would be 10 times e to the minus 0.0462 t. Okay? So there we go. All right? So we're getting a negative interest rate here. Okay? You can think about it that way. Yep, you're losing money. Okay? It's not money, of course. It's actually radioactive material. Anyways, what did we want? We wanted to know how long it would take for the amount to become 1.2 kilos. Okay? Now, technically, there's kilos on both sides here, so when I divide, that would end up canceling, giving us pure numbers here in the end. Okay? Divide on both sides by 10. Let's go ahead and just do that on our heads. We know we just moved the decimal point over one place to the left here. Okay. Okay. Now, can you solve that? This would mean this thing, the exponent times t, would be the natural logarithm of 0.12. And we talked about how nice it is to have the 0 in front of the decimal point when that occurs here. What's t going to be? It's going to be the ratio of these two things. Once again, we're going to get a negative numerator when we perform this calculation. So the whole thing becomes a positive number, of course. It's going to take a positive amount of time. Okay, 0.12 divided by negative 0.0462. And then we'll round to like the nearest tenth of a, what is this? Days, wasn't it? Okay, 45.9 days it looks like to me. So t would be about 45.9 days. You see how it's not quite so important to usually, I mean, unless I have no reason why, but usually I would just go to a tenth of a day or something like that. Is it necessary to know the exact hour, minute, second when you're going to get there? I suppose that depends on the actual applied problem. Okay? Anyways, I think this will do you for now. Okay? You should know the two approaches here. By the way, with this approach here, how would we have approached it using our method, which I actually prefer, is our previous method from the last video. We would say the amount as a function of time is the initial amount, which is 10. Okay, this is being halved over and over again. Use decimals if you want, 0.5. T divided by what? Every 15 days. If I was to work the problem that way, I would get exactly the same answer. Okay? Alrighty. Well, I hope this helps.